Okay, here we're going to talk about antiderivatives. This is another little piece of material that was in the section in the book on mean value theorem that I wanted to add before you did your 5.1 mean value theorem homework on Math Excel. And a corollary in our book is like a definition. I don't know why they don't call it a definition, but I think it's because they're not defining one thing. I think it's like defining a concept. So our corollary 2 is functions with f prime equal 0 are constant. Okay, that is what corollary 2 is about. So basically it says that if f prime of x equals equals 0 at each point of an interval, they're going to call that interval capital I, then there is a constant c for which f of x equals c for all x and I. Now, when we're talking about antiderivatives, we're not talking about setting a derivative equal to 0. We're talking about literally that the derivative is 0. So like on the lesson that we did before, we had y equals x squared, and we took the derivative. We got y prime equals 2x, and we set it equal to 0. We're not talking about that. We're literally taking the derivative, and it's 0. So the only time this is going to happen is when that function is y equals some, y equals a or b or c. I don't care. Any number, you can let it equal anything, but it's going to be a horizontal line. Because if I took a point and I said, okay, find the derivative at that point, the slope of the tangent line is going to be the slope of that line, and it doesn't move on from y values. So the y value, the change in y value is 0. And you know that slope is change in y over change in x. And so if there's no change in y, then your slope is 0. Well, that happens on a horizontal line. So if I tell you that, hey, I've got this function, I don't know what it is, but the derivative is 0, you know. So if given that the derivative is 0, like that's, it's not like x squared equals 0, it's just 0, then you know that f of x is some constant c. I'll put where c is some constant. F of x equals c, where c is some constant. When we start talking about antiderivatives, we're going to be giving you derivatives. We're going to give you the derivative. You're not going to know what the beginning function is, okay? When we do this, we also have corollary 3. Before we start getting into explanations, our corollary 3, functions with the same derivative differ by a constant. And so what that means is if f prime of x equals g prime of x at each point of an interval I, then there is a constant c such that f of x equals g of x plus c for all x in I. Okay, and so that also is something that I'm going to use an example to show you. Okay, so our example number 1, find the derivative of each function. So I'm kind of going back to finding the derivative, but then we're going to talk about what if you were given only the derivative. So if we find the derivative of f of x equals x squared plus 5, this would be f prime of x equals 2x. If we found the derivative of g of x equals x squared minus 3, our g prime of x is just 2x. So if I told you I have a function, so, you know, since we know this, we can see that they both have the same derivative and they're clearly not the same function. So if I just, you know, gave you, hey, f prime of x is 2x, and I said, so that's like you're given, and I said, you know, what would f of x be? What is f of x? Or what would sorry, I said that weird. What is f of x if I told you that the derivative was 2x? And you're like, well, it could be x squared plus 5. It could be x squared minus 3. We know it would be x squared though. Okay, so, and this is how you would be thinking about that. You'd be thinking, well, right now I've got 2x to the 1. And that's after I would have subtracted 1. So I want to add that 1 back in. And I would have multiplied by whatever that subtraction was. So now I'm going to undo that and I'm going to divide by it. So you're adding 1 and you're then dividing by that 1 plus 1. And then that's how you end up with seeing that your original function would have been x squared. But what about the negative 3 or the positive 5? So you're going to have to say, plus it could be some positive or negative constant. So this is what we're going to say our f of x would have been. We're going to say, well, I know that when I take the derivative of x squared, I get 2x, but then there could have been some constant there. Now, it could have been 0, and then it would have just been x squared, or it could have been positive 5, or it could have been negative 3, right? So this we call a family of functions. So if you had to, you know, think about what it looks like, it's like, well, it could have been, you know, that at 0. It could be at 1. It could be at negative 1. It could be, so you can see how it's like a family, and I know that this is hard to see, but it's like a family of functions. It could be any of these functions. If I gave you, if you were given just 1 point, you could find the particular function. Okay, because right now this is a family, okay? And if you're not given a point, you have to just write it as a family. But if I would have said, you know, that f prime of x is 2x, what is f of x if it passes through 1, 2? I could have worded it like that. Then I still would have said that my f of x was x squared plus c, but then I would have put in 2 equals 1 squared plus c. So 2 equals 1 plus c, and I would have solved for c. My c is 1. Here is my particular function based on that given point. This is called an initial value problem. Okay, and you can always, when you're given a function, given a derivative and a point, you can always find the particular function. Okay, so the definition of an antiderivative, according to your calculus book: a function, capital F of x, is an antiderivative of a function, lowercase f of x, if the derivative of capital F equals f of x for all x in the domain of f. The process of finding an antiderivative is antidifferentiation. And basically, you are just going backwards. Your answer, you can always take the derivative of and see if it works. So what I mean by that is, when we were given that f prime of x equals 2x, and we said, okay, well that means our f of x equals x squared plus c, I can always take the derivative of that and see if I get back. So I can say, well, is f prime of x equal to 2x? And I can say, oh, well, let's calculate it. 2x, and then the derivative of a constant would be 0. So yes, it is. So you can always check your answer on these. A lot of times we show, and I'm going to do another example here. A lot of times, instead of doing f prime, we do dy dx. And this, usually when it's written like that, although you can change that to df dx, or you can always change y prime into dy dx, this is considered a differential equation because they've given you the derivative, and we can separate them. So if we started out with dy dx equals 3x squared, we know that that is my derivative. I can multiply by dx on both sides and then use my little integration symbol, because antidifferentiation is integration. So if I wanted to take this, I could also call it this is integration. Okay, oops, sorry. And so that's what that means. And look, this is, I can't get that black one to go on. There we go. This right here is 1. So if I took the derivative of something and got 1, and I'm doing it with respect to y, what would this have been? Well, it would have been y. So is the derivative of y 1? Yes. And see, this is what is telling you what you're doing it with respect to. So when you see this integration symbol, I want you to be thinking that this is your derivative. Okay, so this is my derivative. because I'm looking at an integration symbol. And so I have to figure out what would have given me this derivative. Okay? So let's go back to what we were trying to remember. We said, well, we're going to have to, because we would have subtracted 1. So we want to go back and add 1. We would have brought it down and multiplied. So we want to divide by that because we're undoing that derivative. And remember, if I was taking the derivative of x to the n, we would have brought the n down times x to the n minus 1. Well, now we're trying to undo that. That's why we added 1 here. And then instead of multiplying by n, we are dividing by it. So we can see that this becomes 3x to the third over 3, and my 3's cancel. We can't forget our plus c when we're doing this, though. So this becomes x cubed plus c. This is a family of functions. We don't know what that, constant is. So if I was integrating here, I'd be thinking, well, what would give me that derivative? Oh, x cubed. So this is the same thing over here. This guy right here. We just aren't there yet using these symbols, but I wanted to show you that you are actually integrating. So now let's do example number 3. dy dx equals 4x to the 5th. So my y, I've got my 4x to the 5th. I'm adding 1, and then I'm dividing by that 5 plus 1. And so, and plus c. And so this gives me 4x to the 6th over 6 plus c. Well, divide by 2, divide by 2. So this gives me 2/3 x to the 6th plus c. Now, let's check ourselves. So I'm going to do that in blue. Oh, goodness. So let's check. If I take the derivative of 2/3 x to the 6th plus c, what would I get? Well, I would bring my 6 down times x to the 5th, and then the derivative of a constant is 0. So divide by 3, I get 1. Divide by 3, I get 2. This gives me 4x to the 5th. Okay, and that does equal what I started with. So that means that my answer is good. Okay, you can always do that when you're answering these. So it's kind of nice. Example number 4. dy dx equals 5e to the x. Okay, well, I want you guys to remember that, if I was taking the derivative of 5e to the x, I could bring the 5 out in front times the derivative of e to the x, and that's still going to get me 5e to the x. And so my y here is going to be equal to 5e to the x plus some constant. Because on e to the x, it's kind of just like a different animal because the derivative is, e to the x. And if you've got something being multiplied by it, then your derivative is actually going to be that same thing, okay? So if I wanted to check this, so let's say, okay, now I'm going to go and I'm going to check my answer. And I say my y prime would be, this would be 5e to the x, and then my constant would be 0. So there's my derivative. So it does check out that I get the same thing that I started with. Okay. Example number 5. dy dx equals 2 cosine x. Okay, so I have to be thinking, what could I take the derivative of that gave me cosine? Because, you're remembering this is your derivative. And, if you wanted to separate it, like we did, and integrate, and then you say, okay, my y is equal to, and you could bring your 2 out, what, so if this is your derivative, what can I take the derivative of that gives me cosine? That would be sine. And then plus some constant, because there could have been a constant there. So, if doing it using this is a little bit better because you can bring that constant out in front, we could have done the same thing over here. We could have said, up here on example number 4, we could have said 5 dy equals 5 e to the x dx. We could have integrated. We could have said y equals, and we could have brought that 5 out in front. Integral of e to the x dx. Well, the integral of e to the x is e to the x. So our y would have been 5 e to the x plus c. This might have made more sense to some of you. Just like this might make more sense to some of you. But, at this point, we're just saying, hey, if this was my derivative, what would my original function have been? It's okay, Henry. And so that would have been your answer there. Hold on, bud. Hold on, you're going to have to wait. So example number 6, dy dx equals. Caroline, can you take him out? 2x cubed plus sine x plus 1. Now this is your derivative, okay? So if you wanted to think of it in terms of separating it, can you take him out? 2x cubed plus sine x plus 1 dx, and then integrating both sides, y equals, you could separate these into separate integrals. Like when there's plus or minus in between them, you can make them separate. You just have to put a dx after each one, and this would just be 1 dx. And so you can bring the 2 in front if you wanted to, like that. The derivative that would give you sine would be negative cosine. And then this would just be plus x, because what gives you 1? Well, that would just be 1x. And so this one would be x to the 4th over 4. And then we have minus cosine x plus x. Oops, I forgot my plus c there, plus c. And then your divide by 2, I get 1. Divide by 2, I get 2. Y equals 1/2 x to the 4th minus cosine x plus c. This would be your answer. Here, if you were just trying to do it, from thinking about it, you would have done, to the 3 plus 1 over 3 plus 1. You would have said, oh, this is going to be negative cosine to give me positive sine. And then 1 is x plus c. So, it's the same thing, only this is more, formal. And if you're maybe thinking that the formality of it is easier for you, which some kids might, say that, hey, it's easier for me to, do it more formal to get the answer. But either way, you're going to get that same answer. Okay? Example number 7. Giving you that derivative, dy dx equals 1 over x minus 2. So think about what gives, when you would be, taking the derivative of something, and it would be 1 over that value, u, right? And that makes me think of ln u. So, and times u prime then, if that wasn't just an x. So my thought here is going to be ln absolute value, because you can't have negatives, of x minus 2 plus some constant. And you remember your u prime here, if your u is x minus 2, your u prime is just going to be 1. So that works. Okay? Sorry, that didn't look very nice there. But like I said, your u prime is just 1. So it works out that this could be your derivative. And then go ahead and check yourself. Oops. What is y prime? Oh, well, that would be 1 over x minus 2 times the derivative of x minus 2. And then the derivative of the constant would be 0. So your derivative would just be 1 over x minus 2. So it does check out. So these are all the different types that you might see when you are, all the different type when you're given that differential equation. So, all right. And, this would also be if, I took one of these problems and I gave you an initial value. So, what if I went back up to example number 3? I'm just going to put a little line here. And I said, not only did I give you this derivative 4x to the 5th, but I told you that it was going through the point 0, 3. Well, you would have to say, okay, this would be 4x to the 6th divided by 6 plus some constant. And then, you would have told me 2/3 x to the 6th plus some constant. But then you would have put your 3 and your 0 in. Your 0 in for x and your 3 in for y. And then you would have seen that your c is 3. And so then you could give me the particular solution with my c value. So if you're given a point, you can find that specific c and give me a particular solution, not just a family of functions, okay, when you're given that. So again, one more and then we're done. If I would have given you on example number 6, which was this derivative, and we said that the answer, what did we say the answer was to 6? 1/2 x to the 4th minus cosine x plus c. We said that was our answer, but what if I said it goes through the point 0, -2? Then I would have said, okay, well, -2 equals, and I would have had 1/2 times 0 to the 4th minus the cosine of 0 plus c. Cosine of 0 is 1. Remember that. So -2 equals, now that's going to go to 0. This would be -1 plus c. I would have added 1 to both sides, and my c would have been -1. And then I would have been able to give the particular solution. Y equals 1/2 x to the 4th minus cosine x plus x minus 1. So I put -1 in for c, and that is my particular solution to that differential equation. Okay, because like I said, this right here is your differential equation. Okay, and that point is an initial value. And so those are called initial value problems, and you're solving a differential equation by telling me what function that would have been.